Hello everyone, my name is Alexander Michenko, and my presentation also will be about emerging turbulence. First of all, turbulence is very ubiquitous in our universe. It was firstly described by Leonardo da Vinci in his sketches almost like 500 years ago, and it was also very fascinating. It was called before the Enrico Magoro described in his 1941 paper. Later, in 1941, Enrico Magoro published his paper where he described the energy cascades and how the energy transitions from the injection scale to the inertial scale, and how it later evolves with the famous Magoro formula. In the inertial-range, as you might see, there is a constant energy transfer slope. So later, after the publishing his paper, the interest in the energy turbulence arose, and it started to develop. Transferring from the hydrodynamic turbulence to the MHD turbulence, we add magnetic field, and we see the applications in different parts of the astrophysics, such as emissions that we will describe in this paper. For example, emission turbulence finds its applications in both clusters of galaxies, interstellar meteor, and galaxy star formation. To analyze emission turbulence, different projects appear, such as OHR and different others. Basically, they're working on obtaining the polarization maps and later recovering the 3D magnetic spectrum based on them. And as an example of how the polarization maps are occurred, here is the image of the Planck collaboration, where they obtain the Stokes parameters of Q and Q and the intensity of the magnetic field. So it could be later interesting and useful to analyze the magnetic turbulence flow. In our research, we will consider the separated screen of the synchrotron Faraday emitting screen, and the mixed case when both the emission synchrotron screens appear in the same units of volume. For the separated screen, we'll have separated synchrotron emission screen and Faraday emission screen. So the synchrotron emission screen, it could be represented, for example, as galactical gala, and the effect that so the data that came from the synchrotron screen is later propagated by the Faraday screen that is distanced by with some distance. In the mixed volume, it represents a more complicated regime where the emission and rotation occurs at the same elements of volume, and the total polarization can be defined by the integral of both those parameters rather than the sum. To analyze the recovery of the magnetic turbulence from the polarization maps, we introduce a new measure and call it polarization-angle directional correlation. And here we'll show you how this measure shows and complements the previous measures, such as Lazayan 2016. So it's represented as sum of Fourier transform of both sine and cosine of tilde psi, where psi is the polarization angle. And projection it on the simplest case of the separated screen, we see that the polarization model could be represented, the polarization angle could be represented as the sum of the vectors that contributed by the rotation measure that is proportional to the wave number squared, and also the emission but that is built based on the synchrotron-emitted screen. And we also introduce a measure that will show the transitional criteria, where the sigma of rotation measure corresponds to the standard deviation of the rotation measure, and it shows in which regime the observers obtain their data and analyze it, in which regime they currently are, whether they are in the synchrotron-dominated screen or Faraday-dominated screen, or if it is of the order of one, it is a transitional regime. The polarization of two vectors could be found as a multiplication of the factor of the constants, and also the correlation function of the rotational measures. So our analytical prediction we tested with the simulation design, which was analyzed using the subarachnoid turbulence with MA 0.8 and also all the intensive cubes based on just Kolmogorov-Power law. And later we compared it to the previously known measures. After the completing the simulations, the polarization maps were occurred with Stokes parameters, because Stokes parameters are very convenient to obtaining the polarization angle, and later the polarization map used to recover the magnetic spectrum. Here we can see how in general the polarization maps changes with different lambda and corresponding regimes. So we start with synchrotron-dominated screen, and later with the increase of wave number of wavelength, so we go to the transitional regime, and later to Faraday-dominated screen, where we see the more complicated structures in the polarization angle. After getting the polarization maps, we obtain the polarization angle, the map of the polarization angle, and we implement the directional spectrum method that we introduced. As you can see, there are three distinct regimes represented by the injection and inertial scales, and we see that by taking K averaging, right? So if we take a closer look, we took K shells, which were from minus L over 2 to L over 2. Wave numbers, and later we took K averaging to obtain the directional spectrum. And what was shown is that initially it starts with Kolmogorov-Power law of minus 11 over 3 for the three-dimensional case, and later it starts to break, and distinct slopes appear. For example, in the transitional regime, it's clearly shown that it follows the minus 3 plus MF, which is shown at least in our manuscript. And when we compare this to the synchrotron-dominated screen, we see that in the range from KF to KI, it becomes more shallower, and when we go to the Faraday-dominated screens, it becomes almost flat. In the previous studies, other complementary measures were introduced, such as polarization frequency analysis, polarization spectral analysis, and integrity of the PSA. And we consider this comparison of the directional spectrum, and it shows that it's complementary to the previous known measures. For example, polarization frequency analysis, as here is the reproduction of the Zhang 2016 paper. We show that this position regime follows the lambda minus 2 law, and polarization spectral analysis shows better correlation in the small angle as a small wavelength, which corresponds to the synchrotron-dominated screen, while our measures showed better correlation, showed it better in the Faraday-dominated screen, and which was complementary to the measures. We introduced a new measure and considered was separated in more complicated mixed volume case, and we compared it to the previous known measures such as polarization specialized, polarization frequency analysis, and derivative of PSA, and showed that the newly introduced measure is complementary to the previous ones. Yet with the future development might be interesting in terms of comparison with experimental data, as well as such as LOFAR and other telescope comparison, as well as future comparison with other measures. Okay, thank you very much. And also I would like to thank you my collaborators, Alex Lazarian and Dmitry Bogasyan, who also contributed to this research. Thank you very much.